So maybe I should introduce myself since I actually have a microphone. So yes, it's my pleasure to introduce Michael Larsen of Indiana University, who will talk about character bounds for finite simple groups of Lie type. So let me say, first of all, let me thank everybody who made this talk possible for doing it. I mean, talking in person is more exciting than I would have believed if you had asked me about it 15 months ago. This is the first time I've done it. They'll only see the center board. Okay, so I'll just write on the center board. Okay, very good. So, so as I say, what I want to talk about is closely related. In fact, it's really the same work as Tiep talked about in a recent colloquium here. But I'll try not to do too much overlap, but I won't assume that you've seen it. So this is one of these things where sometimes you can count the same thing in two different ways. And that's a useful thing to do when you can, if they're really different. And so there are different kinds of examples that I'm interested in, but I'll really just talk about one. So let me start on the geometry end. So let G be a simple algebraic group.
Professor, before you get too deep into it, can you move the mic a little bit closer? Is it possible?
Yeah. Okay. Let's see. Yeah, maybe the mask is. Let's see.
Right.
Let's try this. Is this better?
I think it's about the same, but
about the same. Oh, take off this. Yeah, that could help. Okay, let's try this again. I think you have. Dang.
How about if you clip it to your mask?
Well, that's an interesting idea. Okay, let's try that. How about this? Is this better?
yeah, that's better.
Yes.
Okay, great. Okay, so G is a simple algebraic group, let's say over a field K. And we have conjugacy classes x1 through xn. And there's a product map from x1 times dot 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 times xn to G. You have a morphism of varieties in this way. And you can look at this. You can look at points over K. You can ask the following question. Well, there are different versions of the question. You could ask, for example, whether this is surjective. I'll ask maybe a simpler question. Does this hit the identity? Can the identity be written as a product of representatives of these n conjugacy classes? Okay, so that's the question I want to talk about. And of course, if the sum of the dimensions is less than the dimension of G, then you would expect the answer is no. And if it's greater than or equal to G, at least you have a chance. And the feeling might be, or at least it would be reasonable to hope, that if the sum of the dimensions is much larger than the dimension of G, this might imply that 1 is a product that 1 lies in the image of this map. Right? So that's what we might hope for. Probably it depends on the field K. So let me point out. So let me first maybe state what I would consider to be a good version of this theorem. I mean, you might ask for more, but let's say property P, the product, so K has property P, means that there exists C such that for all G over K and for all choices of conjugacy class, if the sum of the dimensions of the xi is greater than C times the dimension of G, this implies that 1 is a product. You can ask which fields have property pk. And so, I mean, you have to be a little bit, can't be too optimistic about this. I mean, it's certainly not true for all fields. I'll give an example. So R does not have this property. How do we know? Well, let's let G be equal to SU2. So here's a picture of SU2. Here's the identity. And we give ourselves a bunch of very small conjugacy classes, and then one really big conjugacy class. Okay? So in this case, clearly, the answer is no. So another example, really it's essentially the same example. PQP is not true. You can do the same thing with the norm 1 elements of a division algebra over QP. Same argument applies. Okay, so so is this ever true? So I mean, everything I'm going to talk about today is joint with Tiep. Some is joint with other people as well. I'll say that. But, so the following thing is true. PFQ is true for all finite fields FQ. And as a corollary, well, I could say PK is true for all algebraically closed fields. In particular, it's true for C. A consequence of the earlier statements is that it's never true for finitely generated extensions of Q, fields which are finitely generated over Q, but it is true for C. And the proof that it's true for C goes through the proof that it's true for FQ. Okay, so that's if you will, the geometry part of this, which at least to me, maybe there's a direct way to see something like this, which doesn't go through the finite field thing and point counting, but I don't see it.
You try to determine the number of products?
Yeah, so of course, it would be very interesting to know the number. And in fact, I mean, the same methods which enable you to show that the set is non-empty generally allow you to say quite accurately that the number of representations over a finite field is about what you would expect. Yeah.
Do you think over C that it's surjective? So
it is surjective. I mean, if you can prove this statement, the surjectivity follows. Yeah. So, but yes, I mean, so the more that well, I don't see. Yeah, I'm sorry. Yeah, the bigger the greater the amount by which this exceeds this product, the more accurately you can show that the number of representations is what you expect.
I guess I'm asking, do you, like in the wearing problem, do you try to determine what the minimum number is ever? Was that?
I see what you're saying. I mean, yes, that would be extremely desirable. I think it's hard, but I think it's an interesting question, and it's not necessarily out of range.
It depends on Q, the number, or you expect it to depends on Q? On
no. The number is no, it does not depend on Q. It doesn't depend on anything. It's an absolute constant. And it, you know, probably we could make it effective. It would probably be, you know, 10 to the 20 or something. I mean, of course, that's not what it really is, but it's probably really, you know, 2. Yeah. So probably the worst case, honestly, is if you take regular semisimple classes, right? You take 2 regular semisimple classes which are not inverses of each other, so they don't represent 1. I would guess that that's probably the worst case. But you know what we can prove, it falls far short of that. Okay, so I think that's all that I wanted to say. Oh yes, no, I wanted to say one more thing. So about this finite field situation, which people who have thought about this problem, I think, will know, but those of you who haven't thought about it might not know the following fact from from finite group theory. So if C1 through Cn are conjugacy classes in a finite group G, then if you take the set of elements, I don't know, x1 through xn in C1 times Cn, such that x1 times xn is equal to 1, the number of solutions, as it were, it is given by a formula. This is a theorem of Frobenius. Is given by the following formula. First of all, you write down the sort of average number of representations of an element in G. And then, yes, as Peter says, there's a kind of Waring's formula type expression, which is, in this case, a sum over the irreducible characters of G of, this way, chi of C1 times chi of Cn divided by chi of 1 to the n minus 2. And when you think about this sum, there's the trivial character here. So that contributes 1. And if G is, for example, a large finite simple group, well, let's say a group of Lie type, because for example, alternating groups have low degree characters, but somehow the only small degree character of a finite simple group of Lie type is going to be the trivial character. And so the hope is that all the other terms, when chi is not equal to 1, will be negligible compared to the chi equals 1 term. That's the sort of strategy of proof.
Let me ask you a quick question.
Yeah.
Suppose you do this calculation, you fix the conjugacy classes, but you ask for how many representations over growing fq to the n, so you can make a zeta function.
Yeah.
What do you know about that, if anything?
Well, okay, so of course, I mean, there's a geometry point of view which says if you take the fiber over 1 of the morphism, the multiplication morphism, x1 cross dot dot. Oh, so maybe I should just make one sort of technical point. So it's not quite true in general. It's not always true that if you take x as a conjugacy class and you take x of fq, that this is a single conjugacy class in the finite group. I mean, it's not far from being true. So there's some little correction you have to do. But ignoring this and looking at x of fq, what you're looking at is the number of points over fq. You're looking at the zeta function of the fiber of the morphism, multiplication morphism, which lies over 1.
Yes.
So what you're asking is, I think, is what does the character theory tell you, for example, about the dimension or the degrees of the cohomology groups of this fiber? And the answer is, if the dimension of the left side is big compared to the dimension of G, they tell you a lot. I mean, the extent to which the terms other than the trivial character become negligible, once you can prove it at all, it rapidly becomes the case that you can show that the remaining stuff is really, really small. So yeah, I mean, I think that this could in principle be used to say things about, in fact, more than in principle, I think this could be a useful tool to say things about the cohomology with compact support, not only of fibers of this kind, but more generally, for example, if you have a Fuchsian group and you look at the variety of homomorphism from the Fuchsian group to your simple algebraic group. Okay, so I mean, this sort of explains why we want to prove results of the following kind. Want to show that if G is a finite simple group of Lie type, and let's say X in G is non-trivial, and chi, an irreducible character of G, is non-trivial, then absolute value of chi of G is really small compared to chi of 1. Right? We would like a statement of this kind. In fact, what would be very nice, would be if we could prove an exponential bound. If we could prove something like chi of, let's say, xi. I'm sorry? Chi of, yeah, thank you. So it would be very nice if we could prove something like this, that chi of xi is less than or equal to chi of 1 to the power of alpha I for I equals 1 to up to n, where alpha I presumably is going to depend on the dimension of xi, but hopefully it depends on it in a nice way, right? So I mean, if we have something like this, then using this formula up here, we get something like, we're interested in chi of 1 to the power of alpha 1 plus dot 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 plus alpha n divided by chi of 1 to the power of n minus 2. That's an upper bound for the summand. And you want to show that this is very small for chi not equal to 1. And so if you somehow know like, yes, okay. So I'm surprised you asked this question, because I mean, I would ask you this question. Okay. Yeah, so I mean, I think one way of thinking about why one should expect a
Could you repeat the question? We didn't hear it.
So the question is, why would you hope that a bound of this kind, I mean, it's clear that it would be convenient to have a bound of this kind. Why would you expect that you would maybe be able to get a bound of this kind? So, I mean, I think a worthwhile thing perhaps to think about is what we get if you take sum over all irreducible characters of G of, let's say, chi of x absolute value squared, right? And so this is going to be equal to the centralizer of x. Well, I guess it's simply equal to the centralizer of x. And so, I mean, centralizer of x, well, I don't know, maybe I said the order of it, is the same thing as the order of G divided by the order of the conjugacy class of x. So if you know something about the dimension of the conjugacy class of x, and you know the dimension of G, so like this is something like q to the power of the codimension. So I mean, it seems like, at least on average, you're getting a bound of this strength. And so you could hope that, and it's of course a kind of weighted average, but you could hope that something like this is true. All right, so right, that's what we want to do. Let me just make a comment here. So there's a relevant theorem, which is due to Liebig and Shalev. And much stronger things are true if you exclude groups of low rank, but in any case, the following is always true, that if you take the sum over all non-trivial characters, non-trivial irreducible characters of 1 over chi of 1 to the power of 1 plus epsilon, this goes to 0 as your finite simple group goes to infinity. This is true even also for alternating groups. So I mean, this is true for all finite simple groups. A large finite simple group, you basically the zeta function evaluated at 1 plus epsilon goes to 1 as the order of the group goes to infinity. So as long as whatever this is, the sum of the alphas minus n minus 2 or something, as long as that is smaller than -1 minus epsilon, then we do in fact get the kind of bound that we're looking for, right? So that's the strategy. All right, and so I mean, how can we hope to prove a bound of this kind? Well, so first of all, let me tell you what it is exactly that we prove. So we have the following theorem. Again, this is Tiep. So there exists an absolute constant G greater than 0, such that, and let me make sure that I don't write it wrong. So I'll say the following, such that for all finite simple groups G of Lie type, for all irreducible characters, and for all G, or X, I guess I was calling it, in G, the following bound is true. The absolute value of chi of X is less than or equal to chi of 1 to a particular power alpha, which can be expressed in the following way: 1 minus this constant times the ratio of the log of this conjugacy class to the log of G. And if you think about what this ratio means, at least when Q is large, right, this is like, so this thing over here behaves sort of like the dimension of the algebraic conjugacy class of X divided by the dimension of the algebraic group G. I really should have different notation for G and G of Q. I shouldn't call them both G, but and likewise with X. But in any case, so this gives you some kind of relative size of the conjugacy classes, which is very nice. And so you have this constant C, which is greater than 0. And so you do, in fact, get a bound of the kind that you want. You know, when the dimension of X is large, if you had, for example, a regular semisimple element, so in high rank, you could think of this as being almost 1, you get an exponent of 1 minus C. C, unfortunately, I mean, we can figure out what C is effectively, but it's really, really small. It's, you know, I don't know, 10 to the minus 20 or something. So this is not a very good estimate for highly regular elements. But for elements which are very singular, it's at least qualitatively, it's the kind of estimate that we expect. Now, if you talk about quantitative estimates, yes, I mean, in many cases, people can do better. And in fact, you know, there's this paper of Bezrukovnikov and Liebig and Shalev and Tiep, and there's a paper of Taylor and Tiep. So they have bounds which are sort of qualitatively similar to our bound, with much better C, but you pay a price in 2 ways. One is that there is a coefficient here which depends on the dimension of G and grows rapidly with that dimension. And another drawback is that it doesn't apply to all elements. This theorem applies to all elements. Yeah, Rich.
Like that whole exponent is supposed to be positive and near 1.
Well, so I wish it weren't near 1, but the whole exponent is positive. Yeah, I mean, it will in fact be near 1 because our C is crummy, but that's right. So I mean, to use this, you want the sum of these, you know, of these exponents to be like, we'll be adding together n of these numbers, and you want something which is significantly smaller, like it's smaller than n minus 3 or something. So, you know, n is going to have to be really big in practice. Okay. Okay, so that's the theorem. And in the time that remains, I want to say something about the strategy of proof. So the first thing I want to say is,
if you have Sn, is it true?
yeah, so Sn, yeah, there is a similar statement for Sn. I think this exact statement is probably not something we know how to prove, or maybe not even true. Basically, what happens with the situation with Sn is that there are sort of 2 regimes which are well understood. So elements of what I'll call small support, by which I mean that there are only a small number of elements which aren't fixed. There is a more or less optimal bound known, which is due to Müller and Schlager-Puchte. Not sure I'm spelling this correctly. And elements of small support, I'm sorry, of large support. Well, maybe I'll say it this way: elements with a small number of fixed points By small, I mean, let's say n to the 1 minus epsilon. There is a result which is more or less optimal, I think, due to myself and Aner Shalev. In the intermediate range, I'm not quite sure what should happen. It's not really a satisfactory. It's not a good answer. I might be able, if I thought about it, I might be able to give you a better answer. I'll try to.
That helps. Thanks.
Yeah. Okay. So. Okay. Let's see. I guess I should really do this first. But maybe Tiep, you might know off the top of your head. Is this exact statement true?
I was thinking that if the same line too, then probably the most conjecture.
Right. Should be true, right? Which we. I see. So it isn't true in general. Okay. Okay. Thank you. All right. So let me just say that exceptional groups are not a problem. So it's a bound of David Gluck, and I can't remember precisely what the statement is, but it's something like this: that chi of g over, or chi of x over chi of 1 is always less than or equal to, I think it's c over the square root of q. If chi is non-trivial and x is non-trivial. And also chi of x over chi of 1 is less than or equal to some absolute constant, which I'll call, I don't know, it's better than this, but let's say 0.99, again, assuming chi is not equal to 1 and x is not equal to 1. And with these two estimates, you can show this is already enough if G is in bounded dimension to prove that, to prove our character bound. I mean, it's basically, this deals with values of Q which are smaller than C squared. And when C is bigger than C squared, Q is bigger than C squared, this then takes over. So really all we have to think about are classical groups. So the main case is G is a classical group over a finite field. And I mean, I should say, it sort of makes sense when you're thinking about this, not just to think about finite simple groups, but closely related groups. So from our point of view, a key example is GLN of FQ. The statement is true for this. And certainly the character theory of GLN of FQ is easier to describe than any of the actual finite simple groups. Okay, but maybe at this point I should say something about, yeah, okay. So I think the next thing which I should talk about is that for classical groups, and also for Sn, in this case, Sn is a good example to think about. So we have a theory of levels. Of irreducible characters. So if I tell you what it looks like for Sn, I think I think you'll maybe be able to guess how it works for like GLN of FQ. So what is the story here? So Sn has a permutation representation, a permutation character, I'll say, chi. Maybe I'll call it chi 0, let's say. So if chi is any character, any irreducible character of Sn, such that, let's see, either chi 0 or sine times chi 0 is contained as a factor in chi to the m, we say that the level of chi is less than or equal to m. Chi 0 to the m, I'm sorry, yes. That if either chi or sine times chi is contained, yes, I'm sorry, I got my chi 0 and my chi mixed up. Yeah, so the idea is we have this sort of basic character, the n-dimensional character, and we look at powers of it, and we look at factors of those powers, and we allow ourselves to if we like, to multiply by the sign character. So what is the effect of this? So what does a character of level 0 look like? It's either the trivial character or the sign character. What does level 1 look like? Well, it looks like this, or it looks like this. Is a level 1. And level 2, you'd have either a horizontal of size n-2 and 2 more boxes, or you'd have a vertical of size n-2 and 2 more boxes, and so on. Now, when the level is really high, it doesn't. I mean, level is really useful when it's small. I mean, that's maybe kind of the moral, but nevertheless, there's a relationship between level and degree. So I mean, I said what it means to have level less than or equal to m, but of course we choose the smallest m to figure out what the level actually is. Right. So what is the relationship between? Actually, there are sort of two relationships. One is a trivial relationship, and one is an interesting one. So trivially, we have that the degree of chi of 1, is less than or equal to n to the power of the level of chi, because chi 1 up to characters is a factor of so what am I saying? Chi 0 to the m, right? So this is the degree of chi 0. So this is the trivial direction. So what's more interesting is that so there is a non-trivial bound goes in the opposite direction. Right, somehow what we have to say is if you have a character of small degree, then there's a fairly small power of chi 0 which contains this character, either this character or the character times sign. Right? And I mean, another way of saying that equivalent way of saying that in terms of these Young diagrams is if you have a character of low degree, there are sort of two possible reasons it's of low degree. One is that there's a big horizontal which includes almost all the boxes in the Young diagram parameterizing the module, or there's a large vertical that includes almost all the boxes. Right. So of course, what you really need to know if you sort of go back to first principles is you need to have a parameterization of the irreducible characters of Sn, which we do. They're given by partitions. And you need some control over the degrees of a given representation, but you don't need the character values. It's much easier to figure out degrees than it is to figure out character values. Right? That's sort of the idea. And I mean, how would you actually do it in the case of Sn? I mean, I think that there are sort of two reasonable strategies one could employ. Maybe you would employ both. One is you could use the hook length formula and say, well, okay, if you, well, okay, I mean, you sort of think about it. If you don't have either a large horizontal or a large vertical, then your hooks are just not going to be large enough to, so that n factorial divided by the product of the hooks will be small. That would be one possible approach. Another approach would be to try to use branching rules. To say, well, what happens if you have an irreducible character of Sn and you restrict it to Sn minus 1? What are the diagrams that arise? Well, of course, basically what you do is you think about all the ways you could remove one box from the diagram. So if you have a box which doesn't look like this or like this, right, then you can figure out some way of removing a bunch of boxes so it's easy to estimate the degree of the representation, and it's pretty big. So that would be a second strategy, and maybe you use some hybrid strategy. Okay, so that's how you do it for Sn. Now, so there's also a level theory. So for example, for GLN, we use the action on the vector space fq to the n. So this gives a GLN fq acts linearly on fq to the n. This gives a permutation representation. This permutation representation enables us to embed. So this permutation. So you think about the complex permutation representation. So this gives a representation. It's not irreducible, but neither is the n-dimensional representation of Sn. This gives a representation GLN of fq goes to GLQ to the n of c. And you do exactly the same thing with this character that we did with the chi0. And this gives us a theory of levels, and we can again prove both a lower bound and an upper bound that say, basically, so approximately what it says. You have to, so roughly, let me just say, first I'll say for Sn, what the analogous statement is. So for Sn, and again, small characters of Sn, roughly the level of chi is equal to the log of chi of 1 divided by the log of n. And for GLN of fq, roughly, and not just GLN of fq. I mean, you can do the same thing for symplectic or unitary groups or orthogonal groups. Roughly, the level of chi is equal to the log of chi of 1 divided by the log of q to the n, which is, if you like, n times the log q. And in fact, it's known with this sort of level 1 and level 2 characters. I mean, these had been looked at, of course, long ago. We know what these characters look like. Now, the description of what the irreducible characters of classical groups are is much more complicated than the parameterization is harder. But we have the gleomalistic theory. Gives parameterization. Of irreducible characters. And we know something about branching rules and so on. So we are able to prove analogous statements. I'm not saying precisely how close the level is to being the log to the base q to the n of chi of 1, but it's, for our purposes, it's a good enough estimate.
If you're a classical group, and maybe you have a real field, or how has a notion of rank?
Yes.
Is that related to your notion of level at all?
Yes, it is related. It's quite similar. Yeah, I mean,
looks
so I'm not sure. So I should know this but this is actually the kind of thing that Tiep knows better than I. I mean, I know, for example, in the symplectic case.
Yes.
He has a nice. There's a nice.
Yeah, he's got a good description of the size. Yeah.
Right. I mean, you sort of right. So you look at the. this parabolic, and you sort of look at the restriction to the unipotent part, and you look at somehow the rank of the things which occur as characters on here, right? And so this is, yeah, it's essentially, it's very closely related.
Yep.
I'm sorry, the rank of Hau and Gurevich, for people who maybe can't hear you because, yeah.
Yeah, so yeah, I mean, so the one, so this is the thing that they call the U rank. So we look at the action of the rank at the being a parabolic, right? And then then but the this rank is kind of like, you think about it like you take the level, you divide by 2, you take the small function of it. Therefore, it behaves like in a closer way.
You're going to have to repeat this term.
Yeah. So, yeah, I mean, maybe I will, rather than, yeah, okay. So, I mean, I think what Tiep just said is that if you take the, yeah, maybe I won't do justice to it. Let me.
Maybe continue with your lecture. We can talk afterwards.
All right. Okay, so right. So now, what is this? Okay, so once you have a level theory in place, then you can try to prove the basic character bound that I asserted earlier by a kind of dévisage argument. So let me again sort of draw a little diagram. So here we have X is highly singular. Well, X is fairly regular. Here we have chi is small. And here we have chi is large. So by singular, I mean that the centralizer of X is small. I'm sorry, that the centralizer of X is large, which is to say the conjugacy class is small. By regular, I mean the opposite. And so, I mean, when you have so another way of saying it here is this is, the centralizer is small. So we have a character, we have a centralizer bound of characters. We showed that the sum of, I mentioned that the sum of the squares of the character values for fixed X is equal to the order of the centralizer. So that being the case, you see, if X is regular and chi is large, this implies, well, it implies a strong version of our bound. This is a good situation, right? Because chi of 1 is big. We want to show that chi of X is small compared to chi of 1, but it's smaller than C of X, and C of X is small compared to chi of 1. So we get a good, this part of the diagram is easy. And so the question is, how do we modify the argument to cover the remaining cases? And we do it in 2 steps. One is we do a reduction, which enables us to cover also small characters once we know how to do the large characters for a given X. And once we've done this, then we do a further reduction, which enables us to say, okay, if we know how to prove our bound for all regular X, then we should be able to deduce it. That is to say, for all regular X and for all characters, we should be able to deduce it also for singular X and for all characters. Okay, so those are 2 rather different reduction steps. And I want to say a few words about each of them. So the first reduction step reduction to small characters is joint work with Gromik, as well as myself and Yep. And so the idea behind this reduction is the following. So suppose chi is small, and chi of x is larger than it should be. But we know the theorem for characters bigger than of higher degree than chi. Okay, so what do we do? So chi of x is larger than it's supposed to be, so chi squared of x is also large. And we decompose chi squared of x into characters. Now, a key point is that in this decomposition, there can't actually be many characters. The reason there can't be many characters is that chi is of low degree, so it's of low level. Right? And if you're of low level, then it's easy to see. So maybe I say. So for chi of low level, chi squared has few irreducible factors. And the reason is that we know chi, or at least chi, maybe tensor some linear character, is a factor of a low power of a fixed known character. So chi basically is contained in chi 0 to the m. So chi squared is contained in chi 0 to the 2m. And we could actually count the number of irreducible factors in chi 0 to the 2m, because this is a character we understand very well. So actually, in the low level case, when we take chi squared, there are very few factors. These factors could be bigger than chi, or they could be smaller than chi. If they're bigger than chi, then our inequality applies to them by this sort of descending induction. If they're smaller than chi, then no matter how big chi of x is compared to chi of 1, I mean, it can't be bigger than chi of 1 itself, they can't contribute enough to cause trouble. So this is how we do a kind of descending induction for the degree of characters. So the remaining question is, so suppose the result is known for all chi, but only for fairly regular x. I don't mean literally regular semi-simple, I mean, or regular, I mean, but you know, the centralizer is small. What do we do in this case? Well, what we do is we use, again, the Frobenius formula that I wrote down before, but we use it in a slightly different form. So the form that I want to use it in is the following. So if x1, x2, xm are IID random variables, uniform on a conjugacy class, I call the conjugacy class C to not, so we don't confuse it with the random variables, conjugacy class C, then we have the following formula for expectations. The expectation of any chi evaluated at the product of the random variables from x1 to xm, this expectation is equal to the expectation of any one of the random variables, let's say x1, to the power of m, divided by the degree of the character to the power of m minus 1. So if you're trying to, sorry, this doesn't make any sense. I don't mean the expectation of x1. I mean the expectation, of course, of chi of x1. Right, so if you're trying to, yeah, of course, when I say the expectation of chi of x1, x1 is a random variable on C, so this is the same thing as just as chi of C to the m divided by chi of 1 to the m minus 1. So if you're trying to get an upper bound for the size of this, a possible way of approaching this is to try to find an upper bound for the expectation of this. And of course, when you take a product of independent random variables, x1 through xm, I mean, what's going to happen is that they're going to begin to equidistribute. The more factors, the better the distribution, but these will begin to equidistribute over the group. And so if you can, I mean, now we're sort of switching from the character point of view back to the group point of view. If you can prove that this equidistribution takes place rapidly enough, then you can get a good bound of this kind. So, I mean, I guess the point is really the following. So when you take m random variables in this way, distributed over this conjugacy class C, which I think of as a highly singular conjugacy class, when you take this product, sometimes you will get a very singular element, but it doesn't happen very often. And so from a probability theory point of view, we can sort of ignore this when we're trying to compute the expectation. Yes, it's true that in those cases, the character value may be very large, but it happens very seldom. Most of the time, you get a fairly regular element for which the existing results will give us a good bound. And so in this way, I mean, this is we're sort of going backward from the usual way, where usually you go from character bounds to equidistribution results. If you have an equidistribution result already, you can go back and prove a character bound. I'm sorry, is there? Oh. So how do we do this? Well, it would be nice if we could do this in a single step. Somehow, technically, we weren't able to make that work. We had to do it in 2 steps. And I'll just say, I'm almost out. Well, is this a 50-minute talk or a 60-minute talk? 1 hour, okay. So let's define the support of x to be equal to the codimension of the largest eigenspace. Here I'm thinking of x as an element of GLN of FQ, but I mean, if it were a symplectic group or an orthogonal group or something, it would be the same. So it's the codimension of the largest eigenspace. So an element of small support is highly singular. So the first thing is to show something like this, that multiply together. So if x1 through, okay. So let I don't know, let m be equal to the integer part of n divided by the support of x. So if you have an element of small support, this will be a large number. And if you had just support 1, it would be n. If you had support 0, well, then you do the identity, and this statement does not apply in the identity, right? So, so what I want to claim is that if we have x1 times ... times xm, if we have elements of this support and we multiply together enough copies of this conjugacy class that it's sort of the reciprocal of or n over the support, we would expect, roughly speaking, that I mean, of course, if you have like an element, suppose you have an element like this, and you multiply it by an element like this, where all but 1 eigenvalue, obviously, all but 2 eigenvalues are going to be n-1. Clearly, you're going to have to multiply. If you want something regular, you're going to have to multiply together a number of copies, which is sort of comparable to n over the support. But the claim is that if you do that, then most of the time, so then this almost always has, let's say, support, say, greater than or equal to n over 2. Now, of course, you have to quantify this almost always, but basically, you don't end up with a big eigenspace. Almost all the time, you don't end up with a big eigenspace if you multiply together enough copies. That's the first step. And then the second step the second, really last for our purposes, reduction step is if x1 through xm are IID uniform random variables on a conjugacy class of support greater than n/2, and m is larger than a constant, then almost surely, and again, you have to quantify this, the product x1 through xm is highly regular. So with these two kinds of reduction steps, we can go from the extremely singular elements to elements which are only kind of singular, and then with the second step from kind of singular elements to elements which are regular enough that we can apply the result of the first kind. Okay, and I'll stop here.
You mentioned, like, when you just started explaining the idea for the proof that you're using
Right.
and then further, when you got into proof, most of the everything here. So I'm just curious how this, how this two, how they interact with.
So, I mean, so if we're just talking about GLN of FQ, for example, the linguistic then just becomes Green's classification of characters. So if you have a character, so okay, so what does the Green classification say?
Can you repeat the question, maybe?
Yeah, I'm sorry. Yeah, so I think if I understand the question correctly, it's somehow at the beginning I said something about we can use the linguistic theory of characters to get enough control to prove a level theory. And the question is, how would that help with a level theory? Is that more or less? Okay. So, so I mean, in general, yeah. So basically what we want to prove is if a character is of low degree, then I can restrict it from GLN to GLN minus something small, just and then get a one-dimensional character. Right. So I need to be able to prove something like that. Now, so you have to think about why a character is small. So in general, characters are obtained by Hara-Chandra induction from if you have some parabolic like this, and so you know, you're inducing from a parabolic like this, and you're getting something of low degree. So this parabolic basically is the whole group, or you know, maybe it looks something like this. And so we can reduce to the case where basically forgotten the terminology that Green uses, but basically that there's just a single simplex. That the character is associated with a single simplex. Mm-hmm. Now, if the simplex is a degree 1 simplex, then we're in the world of unipotent characters, and we understand these unipotent characters very well. Again, there's a kind of a Hara-Chandra story, which enables us to show that if we have a unipotent character, then we can, which is of low degree, then we can restrict it to something and something of high dimension, of low codimension, and get a one-dimensional character. So finally, we have to think about, well, what happens if we have just a single simplex, but it's of degree greater than 1? And in that case, the degree of the character is high. So so that covers all the cases in the case of GLN. But maybe that gives a sense of the flavor.
I was fascinated by your second step, where you used probability theory backwards to get a individual bound. But in some sense, maybe that's similar to the Rankin method of taking high symmetric powers to get an individual bound that you know so well. You introduce extra parameters, average over those in order to, but if you can get a high power, which is what your M is, I'm just saying, I've never seen that argument done, but then as I was thinking about it, I thought maybe it's similar. Is that true?
Well, so it's funny, I would have thought that you could make a better argument for the similarity of the other half of the argument, where you take the character and you square it.
Maybe.
So, but I mean, in a certain sense, those arguments, I guess, are dual to each other. I don't know. I don't.
I mean, you are using, you took a product and you use positivity, obviously, also in the same way. But you explained very clearly how your equidistribution will get you to your bad elements, which is a feature that seems very group theoretic, right?
Definitely. Yeah.
Oh, very interesting.
Carlos?
Aren't there some kind of other series of groups called like Suzuki?
Yeah. So the Suzuki groups, though, are of bounded rank, so they get covered by them, and the result of Gluck does apply to them also. But that's right. Well, so it doesn't cover the alternating groups. So that's sort of unfortunate. And what Tiep said, and I think we certainly discussed it, and I think he's right about that. We came to the same conclusion. I think what we can expect in the case of alternating groups is a little worse. I mean, I think it's worse by a factor of log n in the exponent than the kind of estimate that you get for groups of Lie type.
And your constant that you get, what part of the argument makes it worst, so to speak? I mean,
yeah. So I mean, I think that the worst part is when we are trying to do the descending induction in character degrees. I think that's where we lose the most. We weren't trying hard to optimize because we knew we couldn't get a good constant. But I don't think, but I think that's where we lost the most. I mean, I didn't talk about. I mean, I mainly gave as examples what happened with GLN. GLN actually our bound could be quite a bit better, but yeah, for like orthogonal groups.
So what is your number that you wrote down?
Do you remember what it is? Like 10 to the minus 20? Yeah.
Okay. It's not a skews number.
No. It's not crazy. It's just bad. Here, let me give you the microphone for this.
Yeah. So you see that ideally we'd like to see that you can use the Lucy theory to identify the Lucy label of any character of any given level, right? And actually we did it for the GN and GU, but for the similarity group and for the orthogonal group, then we didn't quite succeed in it. Yeah. So, and because well, I mean like for instance, you have to do with Lucy induction, and also another thing is that not every character is uniform, this kind of thing. So therefore we had to find some roundabout way, and then we got like a weaker bound on the how to relate the degree of the character to the level, and that made the the estimate that we had in the paper with Bob and Michael, like you only like not a very optimal one. Well, it works, but it's not the best one. And then with 2 more reduction, then it's making like even like, so we accounted on these errors, and that's why our constant C is so small. Yeah, that's
So now you have to thank yourself.
Oh yeah. So thank you.
Well, since nobody seems to be there, I don't know why, let me thank Michael for a wonderful lecture. And somehow we should have advertised that it's live. Maybe it was advertised live, but I missed that. Anyway, thank you very much. Since nobody else seems to be introducing you, and you're welcome to continue thanking yourself.
No. I was going to thank the audience. I mean, this has really been it's a great audience. I mean, it's a little daunting actually, because there's several people in this audience right in this room who know more about aspects of what I'm talking about than I do. So it's also kind of exciting.